Okay, here we're going to discuss the tension test, which is going to lead to the stress-strain diagram, which is one of the most important properties that we have in mechanics of materials. Okay, so in a tension test, we use a machine over here, and we load a test specimen into the machine. Before we get started, we measure the initial cross-sectional area of the specimen, as well as what we call the gauge length of the specimen. Basically, these are just the initial area, initial length of the specimen. Okay, then basically this machine rips it apart. Okay, it's slowly stretched, measuring both the load that's being caused on it, as well as the elongation, basically how much it's being stretched. And then from those two values, we get what's called the engineering stress and the engineering strain. The engineering stress is whatever the load is divided by the initial area, and the engineering strain is basically that change in length, that elongation, divided by the initial length. Okay. Now we'll talk a little bit later about why we use the initial area, but where the area is going to be shrinking as we increase this load. But we just define the engineering stress, just divide by that initial area. That's all we're concerned with. So once I get this stress and this strain, basically I plot the two, and I get a stress-strain diagram. So I plot the stress versus the strain, okay, and we get a curve that looks something like this. Now this is generally a curve that would look like for steel, okay, but you could do this with any material, but steel is one of the most common. We're gonna describe this as it is here. So the first region we look at is the elastic region. Okay, now we've got a straight line here. This thing's all proportional here. Okay, and we'll talk about the slope of that line in just a little bit. But there is that proportional relationship between stress and strain. This is where we're hanging out most of the time in engineering fields. Okay, up to what we call the yield point, okay, or the proportional limit, the elastic limit, yield stress. This is all the same stuff. We don't want to go beyond here. Okay, so for our purposes, we're generally hanging out down here, because beyond this elastic region, we get into what we call yielding, where basically now the deformation is permanent. In the elastic region, if I unload it, it'll snap back to where it started. Once I go beyond that elastic region into yielding, if I let go of, if I unload it, it's not going to snap back to the way it was. And that's why we don't want to go beyond it and just hang out in the elastic region when at all possible. Now, for steel, this yield is pretty dramatic in the fact that, notice that my strain increases a lot without any increase in stress. So once I hit that yield point for steel, generally steel gives it up and just kind of completely strains out and will not snap back to its original shape. Okay. If I then continue straining this, continuing adding stress, okay, notice it starts increasing again, okay, all the way up to an ultimate stress. The ultimate stress is the highest stress that I can put on the material through this whole process. Okay. Because then after that ultimate stress, that very high stress and the strain hardening, what I get is necking. I don't have a picture of this, but you can check your book. It's basically a localized area decrease, okay, where, just kind of pinches off in one location. The area shrinks greatly, and basically you are on your way to failure, okay? And you can see actually, the area is decreasing so much that my stress doesn't actually increase. Okay. Once I hit that ultimate stress and necking occurs, we're in trouble. This thing is going to fail. Whoops. Excuse me. Now, you'll see this top curve. That's basically the true stress that we're following. Okay. This would be using the actual area rather than the initial area in finding the stress. Now, the reason we don't use that is because, notice, I said we're usually hanging out down here. We don't want to go past yielding, because yielding is where we run into trouble. Okay, and that's when it doesn't snap back, permanent deformation. We don't usually want that in engineering. So we're hanging out back here, okay? Along this elastic region, there's really no difference between the true stress and the engineering stress. So we don't worry about it. We just take the initial area and stick with it. What really happens is, once I go into strain hardening, especially in necking, that area really is a defining factor and will cause the stress to go up very, very much. But again, we're usually hanging down in the elastic region, so we're not going to worry about it. Now, one of the most important properties we get from this is the modulus of elasticity, or Young's modulus, which is actually the slope of the elastic region, right? That's where we have that linear proportional relationship between stress and strain. Okay, so stress equals Young's modulus times the strain. Okay, or Young's modulus is stress over strain, that slope, rise over run. And this is dependent on the material. So the stiffer a material, such as concrete, the higher that modulus of elasticity is. The more flexible a material is, say like rubber, the lower that modulus of elasticity. It's kind of a measure of stiffness of the material. And it's the slope of the elastic region. Now, two types of materials we want to talk about. The first is a ductile material. Ductile material has a relatively large strain and fracture. We're talking like steel. Generally, steel can stretch about 30% before it fails. Okay, rubber could even be more than that. But then something like a ceramic, right? It doesn't really strain at all. Okay, it takes the load until it can't anymore and then just breaks without any elongation. Okay, and basically what that is, we can measure the what we call percent elongation as just the strain at which fracture occurs, which is basically how much does it strain at fracture. Okay, and the larger that is, the more ductile a material is. Okay, now for these ductile materials such as aluminum, there may not be a well-defined yield point. Okay, with steel, there's this well-defined point at which, it gives it up and goes off. Something like aluminum, that doesn't happen. So I have a curve here, a stress-strain curve. You can see it's just kind of a nice little curve. There's no well-defined point. Okay, so a way that we do that is using an offset method, generally a 0.2% offset method. So what I do is I find clearly where it's proportional, find its slope, and then draw a similar line that goes through 0.2% strain or 0.002 strain. Draw that line and see where it intersects with material. I'll call that my yield stress. Okay, so again, this is used when I don't have that well-defined point. I can draw this 2% offset and then draw the slope of a line, see where it intersects, call that my yield stress. It's just a way to kind of get a yield stress when I don't have a well-defined point. Okay, now when I go past that yield point, remember I go into strain hardening. Okay, and remember I've passed yield, so I have permanent deformation. So we can measure that permanent deformation, right? So I load something up, hits a yield point right here, so I'm following a perfect slope here. At which point I keep going, I get to A prime, and I'm in my plastic region. I'm getting that permanent deformation, and then I unload it. Well, what happens then? Well, the material acts just like it did in the proportional limit in the fact that it goes down, it follows that same slope back. Okay, it doesn't follow the curve back, it just goes down. It doesn't follow this curve back, it just goes down at that slope at the modulus of elasticity, all the way down to when my stress again is 0, it's completely unloaded, and the strain that it is at that point is the permanent set. That's that permanent deformation that I've got. Okay, at which point if I load it again, it'll follow right back up this curve, okay, and keep following it as necessary. Okay, but again, this is the permanent set. When I load past yielding and then let go, it falls back at the same slope down to the permanent set, okay, where the stress equals 0. Finally, we're going to talk about brittle materials. Now, brittle material, basically, there's no yielding, right? When it fails, it fails. When it hits a yield stress, a crack will form, and then boom, it fails. So we're looking at something like ceramics, concrete, right? They don't really strain a whole lot. They just break when they hit a point. Now, the difference with this is with brittle materials, generally compression is huge, right? We just talked a little about tension, where I pull it up and then boop, it breaks. Basically no yielding, anything like that. But under compression, it can see a huge amount of things under compression, which is why we use things like concrete for columns and things that are supporting huge compressive loads. So again, stress-strain diagram is one of the most important properties in mechanics materials. Generally, we're looking for the slope of that elastic region. That gives us Young's modulus. And generally, we're also looking for that yield stress, which we don't want to go beyond for fear that we get that permanent deformation that we generally don't want.